So recall cellular chain complex. So this cellular chain complex is given on page 139 of Hatch's book, Algebraic Topology. So you have a sequence of homology groups like this. So you have Hn plus 1, and then you have relative pair Xn plus 1 comma Xn. You go to Hn, Xn comma Xn minus 1, then you go to Hn minus 1, Xn minus 1, Xn minus 2. So this sequence you obtain by gluing together a long exact sequence of pairs. So first you consider pair Xn plus 1 Xn, then Xn Xn minus 1, and so on. So notice this index matches with this index matches here, this index matches here, and you're decreasing from Hn plus 1, you're going to Hn to Hn minus 1, and so on. And your pairs are also changing. So we are taking this as CW complexes. So this Xn we are writing as Xn to denote this Xn as a filtration of our bigger space X. So your space X has filtration like this, standard filtration. Xn contains Xn minus 1, Xn minus 2. So this X, we are talking about a complex on X. So what page 139 of Hatcher shows is that this is nothing but a chain complex. So although you have homology groups here, this is essentially a chain complex. So you can rewrite this. So you rewrite this in terms of chain complexes right here. So you copy everything. These maps remain the same, which you copy down here. And instead of Hn plus 1, you put Cn plus 1 of the entire space X. Anyway, if you see this, you know you're talking about this, because this n plus 1 is Hn plus 1, and the pair here is also Xn plus 1. The second pair is always just one less. So this is nothing but a chain complex. So this is a chain complex on our space X, and we are rewriting it like this, so that it is clear that this is a chain complex. Now you take homology of this chain complex. So you take homology of this. So homology of this complex gives us the homology of the CW complex. So when you're computing the homology of CW complex, we essentially just write chain complex like this. For example, for torus, you write a chain complex like this, but you know that in dimension 0 you just talk about 0 cells. In dimension 1 you just talk about 1 cells. In dimension 2 you talk about the entire 2 cell. So that is what it comes here, and these cells are precisely coming from these relative pairs. So now we are going to redo this using spectral sequences. So let us start with page 0. So first notice our rule for spectral sequences is minus r and r minus 1 for the direction of arrow. So for page 0, r is 0. So you get 0 and minus 1. So 0 is for the column, this is for the row. So you are saying that 0 left and 1 down. So generally it is r left, r minus 1 up. So now you are 0 left and 1 down because you have minus 1 here. So our at the point PQ, this sits here, CP plus Q, XP, XP minus 1. So this matches. So let us see how this looks like on page 0. So this is the fourth column. So this is the fourth column. This obviously goes to 0. There's an arrow coming here. So this is the fourth column. So you have 4 0, 4 1, 4 2. This is the fifth column. You have 5 0, 5 1, 5 2. You have an arrow coming in here. This is the sixth column, and you can see the arrows are going down. Again, it is XP, XP minus 1. So you just have to worry the XP part. The next part is just one less. So this is the fourth column. So you have 4 0, 4 1, 4 2. You have 4 3, 4 3, 4 3 pair. This is the fifth column. So you have pair X5, X4 everywhere. So this is the sixth column. You have the pair X6, X5 everywhere. So again, the complex sits on the anti-diagonal. So say you're talking about sixth part of the complex. So this is 6 plus 0. So this is C6. This is 5 plus 1. So you notice that you have P plus Q here. So this is of the part C6. 4 plus 2, C6 here. But inside corresponds to the column. So all these are part of C6. So it keeps on going like this on the anti-diagonal. So notice that when we first talked about CW complexes, and you can again see this on page 139 of Hatcher, if you talk about x4 comma x3, that is x4 modulo x3, so that is this pair. So this just consists of 4 cells. So this does not live in dimension higher than 4, but this 4 plus 2 is 6, and here you just have 4 cells, so therefore it does not live in higher dimension, so this is 0. Similarly, this is 4 plus 1 5, but this is just 4 cells, so this is also 0. So this is 5 plus 2 7, and you just have 5 cells here, so this is 0. This is 6 cells here, but you have x5 here, x4 here, so this is 0. 6 plus 2 8, you just have 6 here, 0. Similarly here 0. So only non-zero things remain in this 0th row. So the only non-zero complexes are in the 0th row. Everywhere else you have 0. So once you start taking homology of this to go to page 1, so to page 1 you have to take homology of this, so everywhere you will get 0. You'll get 0 here, 0 here, and since this will just remain as such. So on page 1 you will just get these groups, which we are going to rewrite. So this we are going to rewrite as the corresponding homology groups. So this you can rewrite as H4 plus 0, because you're going to write HP plus Q. This is CP plus Q. I'm writing it as P comma Q, but you have to read it as P plus Q. So H4 plus 0, X4, X3. So this is what we are going to read now in the next page. So now we come to page 1. So on page 1 again our rule is minus R and then R minus 1. So page 1 you have minus 1, 1 minus 1, 0. So 1 left and 0 down. So this is how the arrows will go. So page 1 E1 PQ, every entry is HP plus Q XP, XP minus 1, and this way we are writing this is because page 0 we had written like this: E0 PQ was CP plus Q XP, XP minus 1. So now we have this, and this is the way arrow goes. So this gives us the first line, but we know that the only non-zero components lie for Q equals to 0. That is, here the only non-zero components lie, and everywhere else on the page you just have 0. The homology groups are 0, and this we computed from page 0. So we rewrite this as because this Q is just 0 for non-trivial groups, you write it as HP XP XP minus 1, and this is a chain complex, so you re-Christian it as CP of X, so you rename it as this. So this is just a renaming, and this is the secret sauce of spectral sequence also. All the homology groups, they again form a chain complex. So this is what we are writing here. So you have C6, C5, C4, and so on. And again you just have maps like this. So you have maps like this also going on here, but these are inconsequential because they are just going to give you zeros. So this is the structure of page 1. So now you start taking homology of this, and once you take homology of this, on page 2 you will just have homology group sitting here, here, and here, and everything else would be 0. So you now take the homology of this. So this homology comes here, H4, H5, and H6. So on page 2 you just have the homology groups, and again by this rule on page 2 you put R as 2, you get minus 2 and 2 minus 1, 1. So you get 2 left and 1 up. So only non-zero items live here for Q equals to 0, and everywhere else you have 0. So therefore you have stability, because you have 0 going out and 0 coming in into a module. You take its homology, which is just kernel over image. Image is always 0, kernel is the entire space, so you get stability. So after page 2 everything just will look the same. These groups will remain where they are. So page 2, page 3, all the way to page infinity looks the same. So this is how page infinity will look like. So the homology on page 2 is same as on page infinity, and we talked about computing the homology of space on page infinity is nothing but taking the elements in the entry diagonal and their direct sum. So for example, if you want to compute H5, you take elements in the anti-diagonal like this. But this is just h5 of x because all the terms on the anti-diagonal are 0 except this term. So on page infinity, we said that we take the terms 5 0, we also take the term 4 1 because the indices add up to 5, then you take 3 2 and so on. So all these other terms have indices. For index 4 1 you still have 0 because the only non-zero terms lie in this 0th row, in the 0th row. And again on the second row you have everything 0. In the first row you can see everything is 0, so 4 1 would be 0. In the second row everything is 0, so 3 2 would be 0. So only non-zero element is right here, and that is what is the homology of the space. So page 2 collapses. So the secret sauce is that every time you take this differential, you get a chain complex on the next page, and we expect it to stabilize very soon.